Great.
Sometimes it just crashes.
Can maybe try it without camera.
I will switch it off. Share the screen, share the screen. Share the screen. Share screen, yep. So
Натискай линк можно.
So.
Okay, Kamil, we already share links.
Okay, great.
You can start when you're ready.
Okay, so I will start. I will try to proceed with the Jupyter lab. Is it visible enough?
Yes.
I will check on my phone. Perhaps it doesn't. Does it work? So we will be talking about the introduction to Bayesian modeling. My name is Kamil Dedecius. I am from the Czech Academy of Sciences, from the Institute of Information Theory and Automation. Simultaneously, I teach at the Czech Technical University in Prague, the Faculty of Information Technology. If you want to ask anything, feel free to ask on Slido, or if you have any questions later, then there is an email in the slides, dedecius@utia.cz, and feel free to ask there. I will have the Slido application open during the whole lecture, so if you have any questions, ask there, and I will try to answer during the lecture. The aim and the scope, the Bayesian statistics is quite modern nowadays, so people are interested in it, and we should ask why. So this is why first I will describe what the statistical modeling is, because it's all about statistical modeling in Bayesian modeling. And second, I will talk about what's special about the Bayesian viewpoint. Then I will do a small introduction into MCMC. I cannot hear video properly. I will try to tune the sound, but I think Maria, are you there?
Yes, I'm here. Yes.
There is a question about the audio. The sound quality is quite bad. How do you hear me?
I hear good, but
okay. This is not a problem. It's my computer. So and if I go back to the slide, I will talk about the introduction to Markov chain Monte Carlo because it's one of the popular ways to estimate the parameters using a brute force approach. Markov chain Monte Carlo is closely tied with Stan and PyStan. PyStan is an interface, Python interface to Stan. Stan is a software package that allows to decide what the distribution of our knowledge of parameters is. Then I will go through some practical models. Unfortunately, I have to go through more models than I realized to be possible. The reason is simple. In order to be able to use more elaborate models, I would need to explain the deeper principles of Bayesian or statistical modeling. Black rectangles in screen. Wow. Maria, do you see my screen correctly? So
yes,
because there is there is some notice that there are black rectangles in screen. Perhaps it's the Zoom panel here.
Yes.
But
yes.
I don't know how to make it disappear. Dock to bottom.
Then it in the bottom maybe, but it won't disappear. Maybe try maybe. Oh, now. Maybe put this on the right side, like.
But I don't know how.
like this, yes.
Okay, this will work.
Okay.
This will work. We can see and hear you properly. Great. Good to know. So the practical examples. In order to go through practical examples, more elaborate models, you would need solid knowledge of the statistical modeling principles. And these lectures are very short. We have only 4 90-minute sessions. So we are somewhat limited in this. The stuff, you can find it on GitLab. Fit should see that it's the faculty GitLab. It's not the public GitLab, but the repository is free or open to the whole world. Recommended reading. There are many interesting books about the Bayesian statistics. However, if you want to go through Bayesian statistics using Stan for those MCMC things, I strongly recommend John Kruschke's book, Doing Bayesian Data Analysis. This book is very popular and it's called the puppy book because if you look at how it looks like, there are puppies on it. So it's a puppy book and it's very, very famous in the field. So I will go to the introduction. Where is the link to access the notebooks? The link is, yes, thank you, or in Slack. What is it good for? The Bayesian modeling itself is a part of the mathematical modeling because we use mathematical representation of what we want to model, like some phenomena. We may model trajectory or velocity or acceleration of a moving object. If we observe some moving object using a radar, we use mathematical and physical equations for it. We may model spread of a disease, which is quite actual now. We have a COVID era, and we are modeling spread of this COVID. DDoS attacks. If you have a server room with many servers, you are interested in DDoS attacks, whether you are under attack or not. Image denoising. If we undergo say X-ray imaging or MRI, mathematical resonance imaging, there is always some noise, and the purpose here is to remove this noise to have a nice, bright, clear picture. The Bayesian modeling besides its mathematical modeling, it's a branch of statistical modeling. There are several ways how to perform statistical modeling. There are frequentist ways. If you have any course at your university about statistical modeling, it's most likely the frequentist modeling, not the Bayesian one. The statistical modeling is about dealing with phenomena that are somewhat uncertain, that are not deterministic. For instance, wind speed and direction, it changes from second to second. IQ of a randomly chosen person, it's a random thing. Number of particles incident to a detector, whether you have a solar probe or anything, the numbers of particles are random. The randomness or uncertainty is represented in statistical modeling by statistical distributions. You are probably very familiar with normal or Gaussian distribution. The IQ quotient or intelligence quotient follows approximately the Gaussian distribution. But it's an approximation in the region where we mostly operate, because the Gaussian distribution doesn't have limits, so you can virtually if IQ followed exactly the Gaussian distribution, then there would be non-zero probability of meeting a person with negative or extremely big intelligence quotient. Another model is the Bernoulli distribution. It's a distribution which for dichotomous or binary variables like success or failure, or I will then show a ping. We received pong or we did not receive a pong. Next distribution, this very famous, is the Poisson distribution, which serves for counting particles. You have some mean value of particles, of the number of particles that arrive, and this number changes from a moment to another moment. And a Poisson distribution is used for counting these particles. If we count people on a camera image, then we use often the Poisson distribution too. Then there is a beta distribution, which can describe the probability of some event. The beta distribution is a distribution from 0 to 1. The goal generally in statistical modeling is to estimate the model parameters, because we have some mathematical model, which is statistical. We have some parameters in this model which we want to estimate. If we have a linear regression, we want to estimate the regression coefficients. If we have a mixture model, say mixtures of men and women in a group, we may want to estimate the parameters, the proportion of male and female in a group. Once we have a fully known model, we have a full statistical knowledge of the phenomenon of interest. So we may say that if I choose randomly a person from a group of men and women, the probability of selecting a man is a number, say 0.5. Then we can perform things like predictions, forecasting, and so on. Well, this is the Bayesian statistic and not the frequentist statistic. The Bayesian paradigm represents the knowledge of the inferred or estimated quantities, the parameters, by distribution. This is very, very important difference to the frequency statistics. What I don't know and I estimate it, I use a probability distribution to describe my knowledge about this thing. The problem with Bayesian statistics is that it's computationally extremely demanding in many cases. This is why its use was not so widespread until the computers had enough performance. On the other side, the Bayesian results are often much easier to interpret. If you are familiar with confidence regions in frequency statistics, you know that their interpretation is quite hard. Say if you have a confidence interval for the intelligence quotient, it's 100 scale, then the confidence region says that the true mean confidence, true mean intelligence quotient of the population covers some interval from, I think, 85 to, no, it's one standard deviation. So, well, from some number to some number. And these confidence intervals differ from sample to sample, so they are random. But we can say that the true intelligence quotient lies in the confidence interval with probability, say 95%. No, we say that 95% of confidence intervals cover the true value. It's somewhat enigmatic in the frequency statistics. In Bayesian statistics, it's pretty straightforward. If we construct a Bayesian confidence interval, say 95%, we say the true value of the parameter lies in this interval with probability 95%, period. So up to now, it might be a slightly superficial. So we will immerse into the problem. We will start with statistical representation of knowledge, which is the Bayesian thing, the typical Bayesian thing. Our task, let it be, describe probability that our server replies to ping within 10 milliseconds. That's our task. Describe the probability that our server replies to ping within 10 milliseconds. We are Bayesians. So let's say that the first approach would be, let's state it's some number. In this case, I have some number, say 0.8. The probability of obtaining a reply within 10 milliseconds is 80%. So 90% of pings do not arrive within 10 milliseconds. It's just a peak at 0.8. How do we know this? Just from pinging, it's a stable number. Do I know it's exactly 0.8 and nothing else? It's not as 0.79 or 0.9. With no probability, it's with 100% probability 0.8. That's probably not the best thing how to represent this knowledge, because I need to admit that there is some uncertainty about this number. The Bayesian, from the Bayesian viewpoint, we want to quantify this uncertainty. And this is this figure. I say here that the probability of obtaining Pong within 10 milliseconds is 0.8, but I admit that it might be something around this number, something around 0.78, 0.82 probably. If I were less sure about this, it might look like this. I stated the probability of obtaining Pong within 10 milliseconds is 80%. But I admit that it might be from 0.7 to 0.9, this probability. Well, this is how it works. I hope this is a clear concept now. Similarly, here I say, well, this is a very non-symmetric, but still the mean is 0.8. And here I say the Pong is around 0.8. The probability of obtaining within 10 milliseconds is 0.8. But the probability itself might be from 0.4 to 1. So I don't know much what the probability is. I may even say that I don't know absolutely anything about the probability of obtaining Pong within 10 milliseconds. It's from 0 to 1, and no value is preferred. If I do this, then the probability of obtaining Pong within 10 milliseconds is 1. So it's nearly certain or nearly deterministic event. So this is how it works. What is this? What is this graph? I put there 0.80 to 200. What is this plot? I told you that the Bayesians represent the knowledge of some quantities, unknown quantities, by distribution. This is a distribution. This is some distribution that ranges from 0 to 1. It has two parameters, those A's and B's that I changed. And you probably know the Gaussian distribution, the bell-shaped curve. Well, this is the beta distribution. It's not bell-shaped necessarily. It has two parameters. Recall the Gaussian distribution has mean value and variance as its two parameters. The beta distribution has two parameters too, but these are some A and B. These are shape parameters. The beta distribution has a probability density. This is the probability density function of the beta distribution. The probability density function looks like this. This is some normalizing term. It's the beta function. This is why it's beta distribution, because there is a beta function in it. And probability of Pong within 10 milliseconds to the first parameter, and 1 minus probability of Pong. What is it? It's the probability of not obtaining Pong. Probability of failure to the second parameter. The parameters A and B are positive, real numbers. So unfortunately, I don't have any feedback from you because it's one-way, like one-way ticket. I hope this is clear. If you have any questions regarding this, feel free to send it to Slido, and I will try to reply immediately. I would do a poll, but it would cost some time. So, some interesting properties. I already told you that we represent in Bayesian statistics the estimated or unknown phenomena that you want to describe by a probability distribution or probability density function or probability mass function, which is the case of discrete variables, but I will use probability density function as its definition covers the probability mass functions too. What we are interested in this distribution are the measures of location and dispersion. Measures of location. If you are familiar with statistics or probability, you know the mean, mode, and median. The mean value is defined by some integral. It's the mean of the distribution. The mode is the maximum of the probability density function. The median if you click on it, you will see a Wikipedia page. The median is in the middle of the data set. So the mean is in the center of the mass. The median is in the center of the data set, and the mode is in the maximum. If I show you some distribution like this, it's not still the best. 10 and 40. Still not enough, but well, yes. The mean value is the red one, the red line here. It's not the mode. The mode is the maximum here. It differs somewhat. Or this will work, definitely. So the mean value and the mode is in the maximum. So sometimes, this is why we sometimes use the mean value, which is here, and sometimes use the mode. So finding the mode is often easier than calculating the mean value. So these are measures of location. The median is useful too, but it's mostly used in data sets. If you have a data set, not a theoretical distribution, because sometimes there are nested formula there. If you click on comparison on the three, you will it will redirect you to Wikipedia page about the difference between these or among these three. Sometimes use other quantiles like quartiles, which lays in the 25% of the data set and in 75% of the data set, and one of the quartiles is the median. Deciles, percentiles, and so on. Measures of dispersion. If I want to represent my knowledge of some phenomenon as a number, I use either the mode and the maximum or the mean or the median. If I want to express my uncertainty about this value, then I use the variance, or Roman wrote some message. I will read it shortly. If I want to express the uncertainty, then I use the variance or standard deviation. Variance is defined by this formula, and the beta distribution looks like this. And the standard deviation is simply the square root of the variance. This integral is a general definition. This is just for the beta distribution. Here again, the mean and modes are for the beta distribution. The integral here is a general formula which is valid for virtually any distribution. So if I look at the probability density function of the beta distribution, I may use, it was 800 to 200. So here the knowledge is very concentrated. There is a very, very small variance. If I do 80 to 200, there is a higher variance. There is a higher variance. There is someone listening music behind the window. There is more variance, which means less knowledge and more uncertainty. If I do this, 8 to 2, there is even more variance. So more variance, less knowledge about the variable. So Roman wrote strange beta looks like a strange cousin of the binomial distribution. Is there a reason why we used beta in this case? Well, Roman, The question is, beta looks like a strange cousin of the binomial distribution. Is there a reason why we use beta in this case? The binomial distribution is for discrete variable. It's for describing success or failure. In 10 trials, how many successes, how many failures? It's discrete. The beta distribution is a continuous distribution between 0 and 1, and it describes a phenomenon like the probability. It's from 0 to 1, and virtually any number. It's a continuous distribution. Hope it was comprehensible. OK. Já tady učím, mohli byste s tou muzikou někam kousek dál. Děkuju. So sorry, there are people listening to music, so I had to mute them. So these were the measures of location which describe where is the value of the parameter. I don't know, but I want to estimate. And measures of dispersion, which says how much uncertainty is about this parameter. Other measures of dispersion are the range from to, it's not very used in Bayesian statistics, interquartile range, the distance between the lower and the upper quartile, median, absolute deviation, etc. So if I use again the beta distribution and look at the measures, this is beta distribution with parameters 800 and 200. The mean value, the expectation, I hope you are familiar with the notion that expectation and mean value is the same. So the mean value is 0.8. If I used it for my ping example, probability of obtaining pong within 10 milliseconds is 0.8 if I use the mean. If I use the median, it's 0.8 in this case too. The uncertainty is quantified by this variance or its square root, which is the standard deviation. If I change to say 80 to 20, then there is more uncertainty. The variance has increased. Still, the mean value is 0.8. So I still can talk about the probability of obtaining pong within 10 milliseconds is 0.8, 80%. If I used median, it would be, this time it would be slightly different number because the median and the mean value need not be the same number. So this is how it works. Great. Great, Roman. So final remarks to this. Sometimes some measures do not exist. The first figure here is the Gaussian or normal distribution. The Gaussian or normal distribution. Well, they won't be. The lectures won't be available publicly on YouTube. If there will be any recording which will not be public, I don't know, but not publicly. Back to normal distributions. The orange one has smaller variance than the blue one. But they both have the same mean value, which is 0. There is more uncertainty in the blue one due to the higher variance. The blue one or the orange one says that most of the mass is between -5 to +5. The blue one says the most of the mass is between -10 to +10. So there is more uncertainty. In the Gaussian distribution, we have the mode, the maximum here, and the median, the middle, and the mean at the same point. Unfortunately, it doesn't work as this always. This is the Cauchy distribution. It's quite similar to the Gaussian distribution, but it has heavier tails. So the probability of obtaining, say, -500 is quite high. You would probably say that the mode is 0 because it's the maximum. The median is in the middle, it's 0, 2. And it would be interesting whether you guess that the mean value is 0, 2. Unfortunately, it is not, because the mean value is defined by this integral. And this integral does not exist in the case of the Cauchy distribution. It's a so-called degenerate distribution. I don't have a link here to Cauchy, so if you check Cauchy on Wikipedia, you will find the reason why the integral for the mean value doesn't exist. And if the mean value does not exist, the variance does not exist too, because it's a higher order integral. The third case is the gamma distribution. It's an example of a strongly asymmetric distribution. So we have the mode here at 2, here at 0. We have the mean, which is somewhere more to the right, and the median, well, I don't know, somewhere. Well. So this is about the prior distribution. This is how in the Bayesian statistics we do represent our knowledge. This is strongly different to the frequentist viewpoint. The frequentist viewpoint says it's a number and there is some, say, confidence interval or confidence region. But in Bayesian statistics, we say our knowledge of a parameter of something that I don't know, but I want to estimate it, is represented by this distribution. By this distribution, or that distribution doesn't matter, but by some distribution. Well, let's move on to the data model. The data model. Well, we know that we represent the variables of interest by a statistical distribution. Likewise, we know that there is some data model. The data model is some model. You are familiar with linear regression model, with logistic regression model, and maybe with many other models like the autoregressive model or moving average model, which are frequent in of course, time series analysis, mixture models, classification models, decision trees, random forests, and so on. So there are virtually many different data models, and they describe the data. They don't describe the parameters, which I wanted to shed some light on here, but they describe the data. And this is how the knowledge connects with the data model. The data model, say our ping. I talked about the ping and the probability of timely response. So we are pinging a server and estimating the probability that the pong arrives within 10 milliseconds. So it either arrives or not within 10 milliseconds. Arrives 1 or does not arrive 0. Similarly, we may model coin head 1, tail 0, or switch, switched on, switched off, or some phenomenon detected, some phenomenon not detected, 0, 1, nothing else, just two discrete numbers. Binary variable. with some probability of success, some probability P of X being 1, probability that Pong comes within 10 milliseconds. P is probability of X being 1. So we have X equal to 1 with probability P, and logically the rest is probability 1 minus P. If the Pong arrives within 10 milliseconds with probability 80%, it does not arrive with probability 20%. We may combine it into this formula. If you try to set X being 0, then we have P to 0, it's 1, 1 minus P to 1. 1 minus P is probability of X being 0. If we set X being 1, then this is just 1, and P to the 1. So X being 1 is probability P. So we combined this statement about X into a single formula. The formula is the probability mass function, or probability density function, or probability density function, or the Bernoulli distribution. So it's the Bernoulli distribution, distribution of a discrete variable X. So this is our first statistical model on this course. Great. Just for completeness, the mean value of X is P. It might seem somewhat strange. It's the Pong arrives 1, or the Pong does not arrive 0. The mean value is 0.8. 0.8. Is it arrive or not arrive? There's usually some rounding procedure. The variance for this variable the variance for this variable is P times 1 minus P. There was a question when from Iman when this lecture ends. It ends at 4:30. 4:30. Well, 4:30 of my time, so in 45 minutes approximately. So let's try a ping. I'm not sure whether this would work on Windows because it uses a system ping. So here you can see X is equal to 1 because the Pong time was 6.933. I am pinging Google.com and my limit is 10 milliseconds. I will do it several times. Oh, my network is excellent this day. Now 12. So now the Pong did not arrive within 10 milliseconds, so X is equal to 0. So if I assumed that P is relatively constant, which might be in a server room if I'm pinging a closed server in a server room, of course, Google.com is quite far from me. So if P were relatively constant, how do I estimate it? How do I estimate the probability that the Pong will arrive within 10 milliseconds? I will just sketch a solution. It's not written here. I suggest that you try to add some code and try to estimate P. Most likely, you would send, say, 100 pings and then calculate how many of them were replied within 10 milliseconds and do just fraction. So you could say that 90% of 100 pings arrived within 10 or were replied within 10 milliseconds. So the probability is 0.9. But what's the answer here? 0.9. Is it exactly 0.1? 0.9? Of course, it's not. There is some uncertainty, and you want to represent this uncertainty in the Bayesian way. So you might try to do that fraction solution, and I will show you how it works in the Bayesian way shortly. So another example: bunch of pings. It's another model. So let's say one ping is for losers, and we want say 10 pings. I sent 10 pings and check how many pongs did arrive within 10 milliseconds, and then again 10 pings, and again 10 pings. So in this case, I calculate how many pongs, this is y, how many pongs arrived within 10 milliseconds if probability of each pong within 10 milliseconds is p, and there were n pings, 10 pings. So I may quantify the probability that if there were 10 pings, so y is equal to 1, y is equal to 2, up to y is equal to 10. Again, there is a mean and a variance. If you focus on this formula, it's p to the k. Here it was p to x. 1 minus p to 1 minus x, 1 minus p to 1 minus k. So what's changed? K here is the number less or equal to n, the number of successes. And this combination number is the number of all combination of successes and failures if I have n trials and k successes. So each ping is one Bernoulli trials, and we have n trials, each with probability p. Here is the probability mass or probability density function for this case. I have n equal to 10. So 10 pings, and say that the probability of each ping being replied in 10 milliseconds is 50%. In 10 pings, what's the most likely number of pongs within 10 milliseconds? If the probability is 0.5 and I have 10 pings, then most likely I will obtain 5 replies within 10 milliseconds. Less likely with 4 or 6, even less likely with 3 pongs or 7 pongs within 10 milliseconds, and so on. The probability of obtaining 10 successful replies from 10 pings is very low. If I change, say that 0.8, it was my popular number in the previous example, the probability of obtaining pong within 10 milliseconds is 0.8, 80%. Most likely I obtain 8 pongs within 10 trials. And then the probability gets smaller and smaller. So this is how the binomial distribution works. It's how to say, the binomial distribution is a special case of the binomial distribution for one trial, 20% of success, 80% of success, 20% of failure. So the binomial distribution is a special case of the binomial distribution. I'll check whether there are any other questions on Slido. Well, example 1 doesn't work in index error. Does it mean that confidence intervals can be derived from distributions? So here is a question. Does this mean that the confidence intervals can be derived from distributions? Yes. The Bayesian confidence intervals if I construct the Bayesian confidence interval, where is the here? I simply, it's sometimes called the highest probability density region, which says if I want a 95% interval, then I select 95% of the mass, usually symmetrically, and I state that my parameter lays in this interval with probability 95%. Beware, this is very different to frequency statistics, where the confidence intervals, 95% confidence intervals in frequency statistics say that 95% of constructed confidence interval will cover the true parameter. It's very good. It's just to let your brain explode. In the Bayesian way, the 95% confidence interval covers. It's not about frequency of the intervals, it's about the interval itself. So the frequency statistics, it's the Bayesian statistics. Example 1 does not work. Index error, list index out of range. Ooh. It's strange because it works for me. I don't know whether it's possible to attach a picture here. Probably not. I'm not sure how to, maybe regarding example 1, if you can send the question to Slack. So some final remarks. The estimation methods. If you want to estimate this probability, I have 10 pings. I have 10 pings. I obtain some k replies. How to estimate the probability that the ping will be successful? In frequency statistics, there are some methods like method of moments, which measures the sample moments, and maximum likelihood estimators. This is very well known, the maximum likelihood estimators. I will not talk about it because it's somewhat complicated in real cases. The Bayesian estimators are the alternative, and I will focus on them. So the Bayesian approach to inference, how to estimate the probability that a ping will be replied within 10 milliseconds. The Bayesian approach states that the model is uncertain. This is very important. Model is uncertain. George Box had a very celebrated statement. All models are wrong, but some are useful. The model is uncertain. We are not certain about the model. Au contraire, the frequency statistics usually states that the model describes the true reality. The Bayesian approach fixes data, not parameters. This is also very different to frequency statistics, where the parameters are considered as fixed numbers and the data are generated from the model. Here we say that the data are fixed because they are observed, and the parameters have to be inferred because we don't know anything about it. It's not about frequency of data. The parameters are modeled as random variables. This is very important. The parameters in the Bayesian viewpoint are modeled as random variables. So that's why we use probability distributions to describe the knowledge about these parameters. Beware, still there are some fixed variables. They are just numbers. They are not random. They are modeled as random. What is random is the knowledge about these parameters. If you have the IQ quotient, the mean IQ of the population is a fixed number. It's not a random variable. The mean of the true population is fixed. We model it as a random variable because we want to use some measure of uncertainty about what we estimated. Knowledge about parameters is described by prior or posterior distribution. We will talk about it shortly. The parameters of interest are model parameters. We model these parameters by some distribution, and the distribution itself has some parameters. We call them hyperparameters to avoid confusion. So hyperparameters are parameters of a distribution that describes our knowledge of what we want to estimate. Prior knowledge is what we know before incorporating new observations. For instance, if I meet a person, I would usually say that it's his or her IQ intelligence quotient will be between 85 to 115, because it's one standard deviation around the mean. So this is what would I state. And then as I talk with the person, I obtain new observations, new data about how smart he or she is. I incorporate it into my prior information, and then I obtain the posterior knowledge, which may state, wow, this person talks very wisely. It's almost surely he or she has almost surely a higher intelligence quotient than 100. So my posterior knowledge is prior plus some new data, plus some new observation. This is very important. Sometimes I just say it's the same as the people think, same way. If I drive a bicycle, I can say, wow, now I'm riding between 25 and 35 kilometers per hour. This is the prior knowledge. And then I can look at, say, my computer and, wow, it's 31. So then it's my posterior knowledge. You know that if someone kicks you in your leg, it would hurt. So it's the prior knowledge. Mathematically, we have a Bayesian theorem or Bayes theorem, which turns our prior knowledge represented by this pi of the parameter of interest theta. And we have a data model, which is this fx conditioned on theta. This model is, for instance, our Bernoulli distribution describing the ping, successful or not, 0 or 1, given some parameter theta, which in our case is the probability of success. This is my probability of success a priori, before I have any observations, or from past observations, from some historical measurements. If I multiply this by this and do some normalization, because it should be still a probability density function. Recall, it has some mathematical properties like integrating to 1. So I need to normalize. Then I obtain the posterior distribution. So I may state that 50% of pings is successful with some very low certainty. So I use prior distribution, which is centered. Where do I have it? Here, which is centered at 0.5, say 5, bank. This is centered at 0.5, and it has very high variance. Then I do some updating. I incorporate my measurements, and I end with something like this. This is much sharper, or it's sharper. There's a lower variance, and it concentrates around some value, which is my posterior estimate. If I do it again, it may look like this, say. It concentrates again around some value. And I have a solid knowledge now that it's from 0.5, say, to 0.65. So this is how it works. This is how this formula works. It just incorporates new observations, new data into my prior knowledge to obtain a posterior knowledge, and uses a probability distribution to represent it. The normalizing factor here is this f of x is simply the integral of the numerator, and very often we can skip its calculation because it's just about normalization. This is why we often write this formula. First, we write this longer formula in this form because the Bayesians are very lazy people. And this fraction, since this is only for normalization and it's integral of the numerator, we often use the proportionality. This says that p of theta given x is proportional to model times prior. Proportional means after normalization, it would be equal. Isn't it beautiful? So I look at questions. Link example, animals. What if data contain outliers? Is the Bayesian approach sensitive to outliers? Well, Natalia, yes, the Bayesian approach is sensitive to outliers if your model is not correct. It's generally valid. If you have model which doesn't count with outliers, then you're likely to corrupt your inference. And it doesn't matter whether it's Bayesian statistics, frequency statistics, some machine learning methods. If your model does not take this into account, it might fail. It won't fail always, but it might fail. And the Bayesian statistics is this case too. The Cauchy distribution I talked before is very popular for cases where you have outliers, because it has heavy tail. So it admits that there might be values that are far from most of the data. So that's how it works. Well, back to the Bayesian approach. I told you that the pi of theta is the prior information, say prior information about the unknown parameter, which I update by my observations to obtain posterior information. Well, what does it mean? This is one update. And now I obtain new bunch of data. What can I do? In frequency statistics, I can't do virtually anything because there is nothing like prior information. I just need to, say, merge the data sets together and do the inference again. In the Bayesian statistics, I have my posterior from the past analysis, and it contains already some information. Then I might use this posterior as the prior for a subsequent update by new measurements. So then I have a posterior of the unknown parameter that I want to estimate, given the past observations or past data and the more recent data. If I rewrite it using the first formula, I see that it looks like this, and I see that it's valid because it's perfectly equivalent to using the original prior distribution and a product of models. By the way, do you see the likelihood here? If we didn't have the prior here, we might use this for maximum likelihood. But it's the frequency statistics. Here we are in Bayesian statistics. So I have a prior, and I can either update it by both x1 and x2 in one shot, or I can do it sequentially. Just one update and then the later update. It's perfectly equivalent. This is great for online tasks because you don't need to re-estimate from all the data. Maybe you know the floating data window estimation where you have a bunch of data and you still re-estimate on past, say, 100 data points, then again 100 data points, as you obtain new data, you just move this window and drop the older data. In the Bayesian way, you can do it just one by one. You don't need to recalculate for all those past data. Of course, there are some limitations, mostly connected with tractability in computers. But nowadays we have particle filters. This is called, the online estimation is called filtration. And if you have heard about Kalman filtration or particle filtration, that's the Bayesian way how to do it. Here I have one example: Bernoulli model with unknown probability. So it's here again. So no new questions. So the Bernoulli model for a ping with x equal to 0 being failure, x equal to 1 being success, for instance, based on the time of arrival of the pong message, the probability density function or probability mass function looks like this, where p is the probability of success. If 70% of pings and the success p is 0.7. However, we don't know p. We want to estimate it based on data. If we did it in the frequentist way, we would send say 100 pings. We received some proportion of them, and we would stay this number as a p. But no uncertainty. In the Bayesian way, we would proceed with the same 100 pings, but we would use the prior distribution. We are already familiar with the beta distribution. Its probability density function looks like this. There are some parameters a and b. Recall, we don't estimate a and b, we estimate p. P is a parameter of the model. These parameters a and b are parameters of the prior, so we call them hyperparameters. The parameters of the prior or posterior are hyperparameters to avoid confusion with the inferred parameters of the model. We want to estimate the probability of ping being successful, thus the p, using the beta distribution. The beta distribution has some mean, which would serve as our point estimate of the probability of success. It reads this formula, and we want to express the uncertainty using the variance. So the variance is the uncertainty about our value of p. Posterior distribution. So I have a model. If I have one successful ping, then there will be p to 1 because x is 1. 1 minus p to 1 minus 1, which is 0. If I have a failure, then it's p to 0, 1 minus p to 1. So this is the model. The prior distribution, posterior is model times prior, so the prior distribution is the probability density function of the beta distribution, so this formula here. I have to choose A and B, you saw in the beginning of the lecture. So I set, say, 1 and 1, and do some mathematical operations. Here, if I multiply this, recall, this proportionality sign means that I will renormalize later. This is a normalization factor, so I can remove it from the formula. So there is no 1 divided by b, ab. So it's p to the x plus a minus 1. Can you see it here? What a miracle. 1 minus p to the 1 minus x plus b minus 1. 1 minus x plus b minus 1. So I may substitute a plus x to be a1 and b plus 1 minus x to b1. What does this represent? If I shed some light on this, it looks again like the beta distribution. P to a minus 1, 1 minus b, b minus 1. P to a minus 1, 1 minus p to b1 minus 1. So it's proportional to the beta distribution up to the normalizing factor, proportional. We can do a normalization by the beta function here again. So I end with a beta posterior. That's a miracle. Where the first hyperparameter is the original hyperparameter plus x. If I had a success, then a1 is original a incremented by 1. And the b did not change. Vice versa, if I had an unsuccessful ping, then x is 0. A has not changed, and b is incremented by 1. So this a is a counter of successes, and b is a counter of failures, because I can reuse them for another ping. Again, the same formula. Here, this pi of p would be the beta distribution with these hyperparameters. And again, I will add the number of successes or failures, and so on and so on. Beta prior times Bernoulli model yields beta posterior. It's smart. I can do it online even. It's very fast, very quick. Here is an example. I start with a flat prior. 1, 1 looks like, where is the beta distribution? Here. If I start with a prior which looks like this, it's equivalently the uniform prior from 0 to 1, which says my probability of receiving a successful pong is from 0 to 1, and I don't prefer any particular value here. All are the same likely for me. The mean value is, of course, 0.5, but the mean value is equally likely as any other number from 0 to 1. So I start with this and send, say, five pings. Here the success will be if the pong comes within 7 milliseconds. The fair is if it comes within more. So after 5 pings, the first one was uniform. It's not plotted here. Then I had one update. It was successful. Then I had another update, and another and another and another. So so the probability density function looks like this. It's 2 successful. I will change to say 6. Do you see it? The probability of obtaining ping within 6 milliseconds. The first one was uniform. It's not plotted here. After the first update, it looks like the blue line. It was successful. And then the orange one, so it was not successful, and so on and so on. And it tends to the some smaller numbers. The point estimates would be here probably 0.5, here probably something like 0.3, here probably like 0.25, say, and so on. So it concentrates on some number. So I put there again the number 7 and send more pings to see what will happen. 100 pings, we need to wait shortly for the results. So where it is, here it is, where is it? Here it is. So I started with the probability of successful ping being uniform from 0 to 1. It's not plotted here. Then there was an unsuccessful ping, and then there are some successful, some unsuccessful. And what happens? The probability concentrates around some number. First, it's very flat and concentrates. If the probability of successful ping would be constant, which is nonsense here. If it were constant, then in a long run, the probability density function would degenerate to a single point. That would be exactly the probability of ping being successful. So in other words, I see that it estimates my probability of ping being successful, that it comes within 7 milliseconds, and the uncertainty shrinks. This is exactly the same thing that, or the convergence to the true value of the ping being successful is the same asymptotically as the estimate of the frequency statistics of the, say, maximum likelihood estimator. So these two converge, but they converge in different senses. The important thing here in the Bayesian realm is that I can quantify the uncertainty about the estimate. Here, the uncertainty is relatively low. If I look at, say, the green one, I can say that the probability of ping being successful is between 0.75 to 0.9 with probability, say, 95%. So this is how it works. This approach has some downsides. This beta prior times Bernoulli model leads to beta posterior, which can be used as the beta prior for the next update by another Bernoulli model, and so on. This is called a conjugacy, conjugate prior. The beta is the conjugate prior to the Bernoulli model. And unfortunately, the conjugacy is not always present. It's a rather rare case. Fortunately, There are many models where the conjugacy exists. For instance, in linear regression, in Kalman filtration, in estimation of the time to failure, and in many other cases. However, there are cases where conjugate priors do not exist and we need some brute force method or some approximate methods. If we used other prior distribution than the beta prior here for the Bernoulli model, the posterior distribution would not be any standard distribution because Bernoulli times, say, Gaussian distribution does not yield anything standard. And that's a problem because in order to calculate the mean value, just the mean value for the point estimate, you need to integrate. And you need to integrate very strange and nasty integrals often. For this reason, I will present the STAN package, STAN software, where it's possible to do it quite easily. It's also called probabilistic programming. I don't know why programming, but well, probabilistic programming. There are some guidelines how to choose the prior distribution. The most important thing is that the support of the prior distribution should cover the true parameter value. For instance, if I used, instead of the beta distribution, some distribution that's only from 0 to 0.4, then the estimate can't, the posterior distribution can't cover the value 0.85 because it's from 0 to 0.4. The posterior estimate would converge as close as possible, and it will stop at the value 0.4 because it can't anymore approach the true value because the prior is limited to the interval 0 to 0.4. So it's very important to choose the prior wisely. This is quite easy. Another important thing is that the lower knowledge we have, the flatter the prior distribution should be. If I started with distributions, say A being 1, B being 100, then the result would look like, let's wait a few moments. This is quite, the beta distribution with parameters 1 and 100 is quite sharp. And you see that it converges to the true parameter, which was around 0.25. But 100 data was not enough to converge. If I use a flat prior, even say 10, 10, it's still quite flat. It will converge. Let's wait again. So come on. Here it is. You see, it converged. It did not converge. Maybe the pink successfulness changed a bit, but it converged from the blue one, or there was something yet flatter. It converges. So it's very important to choose the prior hyperparameters wisely. Generally, if you choose a flat prior, you will have better results than if you choose a sharper prior. So it's about choosing the parameters A and B. By the way, by checking Slido, I see that there was a question how to choose A and B. For online tasks, we prefer conjugate priors. If they exist, they help us a lot because the result is first analytically available, beta prior times Bernoulli model beta posterior. And it's a standard distribution, which can be again reused for using the standard distribution or for estimation of or for obtaining point estimates. I can look into Wikipedia and search how to calculate the say mean value. If you click at conjugacy, you realize that there are some useful conjugate pairs. Bernoulli beta binomial there's beta conjugate prior. The rate of the Poisson distribution is can be estimated using the gamma distribution. Again, it's a standard distribution. If you have a geometric distribution, we can use beta distribution for estimation of the probability of the geometric distribution. In continuous cases, the normal distribution with known mean, with unknown mean and unknown variance can be estimated using the normal inverse gamma distribution or normal gamma distribution or a normal skate chi-square distribution. Multivariate normal inverse Wishart distribution, Pareto distributions, exponential distributions, and so on. So there are many conjugate pairs, but if you have more complicated models, they unfortunately do not exist often. So this is how to choose the prior distribution. This is the end of the first notebook. So I will move to questions and answers. The first one is how to choose the initial values of A and B. I think I replied to this. If you choose A and B low, then you will obtain a flatter. If A and B is 1, you have completely uninformative, vague prior from 0 to 1, not preferring any particular value. If I use this prior distribution for estimation of the probability of, say, coin being fair, so that the probability of head is 0.5, and I look at the particular coin and say, wow, this coin seems that it might be fair, I can do this. This is relatively concentrated around 0.5, so the coin is fair. But I admit that maybe this is not exactly true. So it might be somewhat unfair. But from observing the particular coin, I would say, no, it's definitely not totally unfair. It does not prefer just heads or tails. If there are some other distributions, the situation gets complicated. If we have a prior distribution which is Gaussian, then we might choose a distribution with very high variance, very flat distribution. If we use asymmetric distributions like the gamma distribution, then we usually need to read some guidelines. And in the next notebook, there is a link to these guidelines, I think. I'm pretty sure it's there because I wrote it there. Well, another question. It's only me having problems with opening 1B, 2A, 2B notebooks directly on GitLab. Well, don't open it directly on GitLab because GitLab has rendering issues. Always download it and run it locally. Even you don't need to run it because the figures are already plotted, but there are always problems with GitLab, and these are generally with GitLab software. Roman, maybe another silly question. No questions are silly. Can't we use central limit theorem in case of normal prior distribution to collect some data points and then just use their normalized sum as an input for Bayesian model to ensure that the posterior is also normal. Well, if you combine the data in this way, you lose the information about how much data points did you use. The central limit theorem states that your variables tend to the normal distribution. Generally, you can exploit the central limit theorem, but I am not. Well, I am sure you will not gain very much from this. It's much better to proceed directly with the data. As you transform data, you may obtain different results, and the central limit theorem is about convergence. So if you have 10 data points, then you can't talk about any convergence. This is an important point, by the way. The Bayesian statistics is very useful if you have few data. If you have few data, let's come here. Say I start with this ping, and I run only 5 pings. So 5 pings, what would state the frequency statistics? 5 pings, say 3 of them successful. Is the probability 3/5? 0.6? 0.6, yes. Probably not. We can't say it's 0.6. How could we dare? In the Bayesian statistics, we obtain the posterior. The posterior, in this case, this magenta one, says it's probably 0. If we used the mode, the maximum 0.8, if we use the mean 0.71. But here I see that the posterior covers quite a lot of region. The 95% Bayesian credibility or confidence interval would most likely cover the interval from 0.3 to 0.95. So I can express that, well, the probability of ping being successful is 0.71, but my uncertainty is huge, absolutely huge. But I have some estimate. In the frequency statistics, we don't have anything like that. It's this easy representation or interpretation. As you mentioned, the distributions converge to true value in different senses in Bayesian and frequency statistics. Can you explain what you meant? Well, Anton, generally, if you have an estimation task, the goal is to estimate the unknown quantity. And you can estimate it using any possible method. But what you want is that the estimates converge to the true value. The frequency statistics uses some methods of moments and maximum likelihood estimates and so on. And you want them to converge to the true value. In Bayesian statistics, we have Bayesian estimators, and they have to converge too. The convergence is a crucial idea here. Of course, there is something called bias. Your estimates might be biased, but still the bias should be the lowest possible. So this is the convergence. When will the second class start? Is there any break? Yes, there is a break. I think that it starts at 5:30. At 5:30 of my time, so after 60 minutes. We end within 30 minutes. So Anton, I hope the answer was clear. The convergence is very crucial. The distribution converge to the true value in different and in different senses. This sense in the frequency statistics is that the point estimate converges. In the Bayesian statistics, it means that if you look at the distribution here, it shrinks and shrinks and shrinks after I will use this. I told you that A is the number of successes, the number of failures. Do you see it? It converges to some number. Oops. Yeah, it's just an axis. It converges to some number. It's not perfectly a point still. It has some support, not just a number, but it converges. If I do this, it looks like this. And the mean is 0.5. If I add an order, it shrinks, and if I run in this way, it shrinks and shrinks and shrinks, and in the limit, it shrinks to a point, degenerates to a point. So this is the convergence in the Bayesian sense. The variance of the posterior distribution the limit is 0. Are there any consistency results for Andrei? Are there any consistency results for Bayesian approach, and what is the rate of convergence to the true distribution? Is it faster than that of maximum likelihood of moment method? Well, there are some consistency results. The problem is that the studies of Bayesian consistency require quite a lot of information theoretical tools. So the consistencies are usually studied from the theory of divergences viewpoint. There are some papers about it. Generally, the topic is highly mathematically technical. If you are interested, drop me an email and I will send you some papers about this. The important thing is that it's that the consistency is guaranteed in most cases. Moreover, I told you about if your prior does not cover the true parameter of interest, the true value of the parameter of interest, the estimates converge as close as possible. So if it's from 0 to 0.4 your prior, and the true value is 0.5, the posterior estimate will converge to the value 0.4. It can't go any farther, but it will go as close as possible. This is proved, I think, using the Kubic-Leibler divergence. So that's it. Well, there are some consistency results. Generally, they are very technical. Generally, the asymptotic properties of the Bayesian estimates are hard to study. Anonymous, what's the benefit of choosing the prior distribution for prior over maximizing a posteriori? What is the benefit of choosing the distribution for prior over maximizing a posteriori? I'm not sure that I understand the question, or maybe I'm sure that I don't understand the question. If the question is, what's the benefit of prior over maximum a posteriori? This is a mix of different things. Maximum a posteriori. If I use, let's say that this. Oh, not this. So another doesn't work too. So let's do this one. Maybe this. So maximum a posteriori. Maximum if this is the posterior, this is a posterior distribution, then the map estimate, maximum a posteriori estimate, is just the mode. In many cases, we have non-standard distributions. Let's say if this looked like stairs, then the maximum a posteriori estimate is quite easy to obtain by maximization. We can use virtually any method that searches for maximum, any numerical methods, any method of say just a method for searching for maximum of a function. This is the maximum a posteriori. It's very easy to use if you have enough computational power. It's straightforward. It's easier than calculating the mean value. Here we have a standard formula for a mean value. But if we multiply the beta distribution by, say, Gaussian distribution, we won't have a formula for the mean of the result, and we would need to calculate it by integration. And it might be very, very complicated if possible. The maximum a posteriori would be easier. We just search for the maximum of the product. It's the maximum a posteriori. So I hoped I answered the question. So any other questions? Seems that there are none. So, well, we can stop here, and let's meet again in 45 minutes. So maybe you see me now. So see you. screen share. So I think we can start again. I would like to ask Maria if she can post me over. I'm unmuted and you can...
Yes, I hear you, Kamil.
Great.
Everything is okay.
Great. So I will go on. Well, we will continue with the second part. Yeah. I'll continue with the second part of today session. The introduction to Bayesian modeling part 1b. So it's another file 1b notebook. I already told you that we can't rely on the conjugate priors in general, but we need to very often we need to use some more brute force techniques to obtain the posterior distributions. The conjugate priors are useful because they are analytically tractable and the form of the distribution is preserved. If you have beta prior and it's conjugated to the model, you end with beta posterior. In many cases, the conjugate priors do not exist, and one of the way how to proceed is with the Markov chain Monte Carlo based inference. Other ways are the maximum a posteriori estimation, but you don't obtain the uncertainty measures usually unless you adopt, say, some Laplace type approximations. Or there is a variational Bayesian inference, which uses the calculus of variations. But again, it's somewhat specific, and you need at least some conjugacy in the same more complicated model. We will focus on Markov chain Monte Carlo because it's quite easy, and there is a software for it which helps you a lot. It helps you so much that even people use the software without understanding what they really do. So I will try to suppress this phenomenon and try to explain how it works. If we try to model something, some process or some event, we proceed generally in 3 steps. First, we have to construct a model that is to decide which distribution do the data obey. Once we have a model, we need to choose a convenient prior distribution or distributions for everything that we want to estimate. And finally, we run estimation and analyze the results. Maybe you could argue that then we can do forecasts and so on. But once you have inferred model, this everything is just your option what to do next. These 3 steps are crucial. We will use STAN, which is a software for sampling from the posterior distribution. It's suitable for some additional things, but we will stick with this. There is a Python interface called PyStan. Usually, or recently, people used matplotlib for visualization of the results. Then someone decided to write a package. It's called Arvis, and it performs all useful visualizations for you. Beside the STAN, there is PyMC3 software, which can do actually the same things for the Bayesian inference. I have the first example here. it's a toy example. Today, there will be merely 2 examples, just for getting familiar with the idea. The first example is about coin tossing. We simulate a number of tosses. The number is given by the n-dot variable, tosses of a coin, or you may say pings, successful, unsuccessful ping, detections of some phenomenon, detected, not detected, switched on, switched off. So it's a binary variable. We simulate this using a known probability of head, success, presence of phenomenon, being switched on, etc., in order to estimate the probability from the data, to see how our estimate converges to the true value. Then we will try to infer this probability from the data. We already know that the binary 0-1 data follow the Bernoulli distribution, the Bernoulli distribution I used for the ping. For this, there is a package inside PyStats. It contains the Bernoulli class, and it has our RVS, random variable sampling method, which provides the pseudo sampling. This is how it looks. We simulate 1,000 data, 1,000 tosses of a coin. A probability of head is 0.7. Now we know this value, but we want to estimate it from the data. Then X is that sampling. We sample from the Bernoulli distribution with probability of P 1,000 samples. If I run it, I have 674 ones or heads, and the rest are tails. The frequentist estimate, which would coincide with the maximum likelihood estimate in this case, is 0.674, or maybe some different number because there is no fixed seed. So now I have 683. Well, this is a frequentist estimate of probability of head, but we can't say what's our certainty or uncertainty in this number. Is it very probable that it's 0.683, or is it more or less unlikely? What is our uncertainty about this number? We will try to analyze it using the Bayesian way. We could use, of course, the beta prior with hyperparameters A and B. We already know that if we add the number of successes or heads to the hyperparameter A and the number of feathers or tails to the hyperparameter B, we end with the beta posterior with hyperparameters A1 and B1. We will check it later, but we want to get familiar with PyStan. Stan is a very robust and very solid software. Our first code will be very simple program, simple code. We will define some blocks. The blocks are given here. Maybe I could increase the size of the font. Close this. The code which defines the model looks like this. The strength here is that for sampling, the sampling, the Markov chain Monte Carlo sampling runs in a huge for cycle. So it's incredibly expensive. Therefore, Stan uses a C++ code, which is much faster. So we need to define the model, and then it's compiled to C++. We have three data blocks here. Three blocks here. One of them is data. It describes data. We have n data items, which is 100 tosses. It's integer, and it's non-negative. Then we have our observations. Our observations are zeros or ones. These are integers, and we have n of them. The next data block, the next model block is about parameters. We have a probability of a Bernoulli distribution, which is a real number between 0 and 1, and it's the probability p. The final block is the model block. It describes what the priors are and what the model is. So I have a prior p. Sorry, I have a parameter p, and the prior for it is beta. I opted for flat 1, 1, beta 1, 1. And then I have n data points, which are Bernoulli distributed with probability p, and that's it. We have defined it in a for cycle. Later we will see that sometimes we can skip the for cycle and use some other definition. If I run it, here it's compiled using Python to the C++ code. This time it's very fast, very quickly compiled. Sometimes the compilation gets very long, much longer. Well, it's still compiled. So during the compilation time, we can check the other cells in the notebook. So we define a Python dictionary for the data block. It's for this data block in the model code. We need to define n and xn. So n is the number of data, and that's our 1000, and x is our x. It's this x. It's still compiling. You can see that it takes time. Such an easy code. Still compiling. So here it is. So our data, and now we have everything necessary. We now perform the inference by sampling from the posterior. Virtually, it means that Python feeds the C++ code by our data, by our simulated tosses, and in the C++ code, Markov chain is used for sampling from the posterior. We can represent any distribution by sampling from it. It approximates the distribution. You know what a histogram is. A histogram is an approximation of a distribution. Here I want to sample from the posterior distribution. For sampling, there is a sampling method which requires the data, which is this, the number of iterations. I have 100,000. Chains is the number of Markov chain Monte Carlo chains. I will explain what a chain is tomorrow. So we will just use one chain. And verbose, well, I always like verbose. So let's see at the result. Let's look at the result. Here it is. It was fast, wasn't it? 100,000 sequential steps of Markov chain Monte Carlo method. So fast, but only due to the C++ code. So here we have inference for Stan model. It's some model represented by something on the disk. I ran one chain. The chain made 100,000 iterations. Warm up was 50,000 steps. The warm up is an initialization. This warm up is dropped usually. I will talk about warm up tomorrow. Thin is a way to suppress autocorrelation. Again, I will talk about details tomorrow. So let's keep it this now. What we have here is the parameter p that I wanted to estimate has mean value 0.68 in the posterior distribution. It's solid. By the way, it's close to the frequentist estimate 0.683 and the true parameter is 0.7. Next, we have SE mean. It's Markov chain standard error. Its interpretation is somewhat tricky. I will not discuss this one. The standard deviation is very tiny. So I'm pretty sure about the mean 0.68. Here are the 2.5 and 97.5 percentiles. Between these two numbers, 0.65 and 0.71, lays 95% of the mass of the posterior probability. So with 95% of probability, P is between 0.65 and 0.71. This is our median, 0.68. Lower quartile and upper quartile. There are 50% of mass. There's 50% of mass between these numbers, 0.68 and 0.69. The number of effective samples, the higher the better. And R hat is the Gelman-Rubin diagnostic. Usually we want value smaller than 1.1. If there were some complications, Stan will do an exclamation here. It will rise. There is a problem. So there is no warning here. I may say that my P, and the point estimate for P is 0.68 if I used mean. And if I used the median, it's 0.682 by coincidence. This is the log probability. Next, we want to look at the results. This is nice. And I can use the number. I have the point estimate and I have some expression for the uncertainty, but I want to see the posterior probability, and I want to say whether the inference was stable. So for this, we have an ARVIS package, visualization package. For its use, we need to to convert the data from PyStan representation to ARVIS representation. We just use the from PyStan and as the posterior say fit. Now we can plot the trace and the estimate of the posterior distribution. So this is the estimate of the posterior distribution. It's a very nice distribution, isn't it? it really resembles the beta prior, or sorry, beta posterior. And it is the beta posterior, by the way. Here is the trace of the chain, how the chain sampled from the posterior. And this figure, you can't see much thing now because you don't want to search for. If it's such a nice hairy line, it means that the sampling was robust and it worked well. Let us now check how similar the result is to the true beta posterior density that was obtained using the raw mathematics, because we know that beta prior is conjugate to the model, and the result is again the beta posterior. So some classical probability distribution. For this, I extract the samples from this chain, and I plot the histogram, which is this blue one. This is the histogram of the chain. Then there is a blue line, which is the trace of the posterior distribution obtained using MCMC. So it's this line, the blue one. And then there is an orange one, which is the analytical posterior, the beta distribution, the analytically obtained beta distribution. And you can see that the simulated and the true analytical posterior are nearly identical. There is some small imprecision here, but it's a very solid result. So this is how it works. So it works. I will answer the questions on Slido. What OS and version of Jupyter do you use? Can I do Bayesian modeling in R as well as in Python? Can you recommend some literature on Bayesian modeling in R? I think that the Krushke's book, the puppy book, works with R and with Stan. The Stan was originally used in R, and the PyStan is just a Python interface to it. OS and version of Jupyter. I use Linux and the version of Jupyter, I think the latest one. Another question. I can open only one AIBNB file and the other files cannot be opened. Do I only have this problem? I think that there is no one else with the problem. It should, if you can clone the repository, then you should be able to open it. Next question. Can you explain what is NF in the summary of fitted Python model? You said it is the number of effective samples. What are the effective samples? What are the ineffective samples? Great, good question. So the number of effective samples is the number of samples that really represent the posterior distributions. The Markov chain Monte Carlo sampler, I will explain tomorrow, proceeds in a way that it generates one sample by one, just one by one. If the new proposed sample is not accepted, the old one is repeated. So this may influence the effectiveness of the sampler. Yeah, that's it. Sometimes the samples represent or are located in regions where there is virtually very low probability density function value. then these samples are not effective too. What we want is that the samples are concentrated in the region where the probability density is concentrated. So that's it. And by the way, and what we want is that the number of effective samples is the highest possible. If we investigate this, total post-warm-up draws is 50,000 and 22,000 are effective. So they really represent the posterior. You may consult this with the STAN user guide. STAN user guide is available on mcstan.org, where everything possible about STAN is described. Whenever I work with STAN, I always have a tab with the STAN user guide opened, because, well, you need to check everything possible. So I suggest for some things to consult this. Sometimes the guide is very superficial. You see the posterior predictive sampling. It looks like this, but well, that's it. Sometimes you need to ask on forums. So there was another question. Where can I find the files, please? If you look at Intro into Bayesian Modeling, there is a link to the repository. I will copy it. It's a GitLab repository, so either clone it or download it. It was Sarah. Anton, so MCMC is used for sampling from the estimated posterior distribution. Yes, it's. I wouldn't say estimated. I would say just from the posterior distribution. In 1A notebook, we had a posterior which looked like, say, this, just one line. And what MCMC does is sampling, say, from the magenta one, is sampling from this distribution, just from the posterior distribution. It samples from it, and once we have samples, we can represent it by some approximation of the true posterior distribution. Here we see the orange one is a true posterior distribution because I know its analytical form here. This is just a toy example. And the blue one, which is somewhat imprecise here, it approximates it. It approximates it. The samples are represented by the histogram, and when we use kernel density to smoothen the histogram, we obtain the blue line here. So what we may change is the number of samples. Say that I will change to I mean iterations of the Markov chain Monte Carlo. If I do just 1,000 iterations, blank. So this is how it looks. Does it resemble the true beta posterior? Of course it does not, because we have only 1,000 samples. Some of them are rejected. The number of effective samples is as low as 200. And if I look at the true, why is it limited to 0.68? If I look at the posterior, it's really far from the true posterior. So the more samples, the more Markov chain Monte Carlo samples, the better. Here we can see how the sampler moves from, say, 0.68, then it samples 0.71, then it samples some other value, and so on and so on. So it's always reasonable to have more samples than just some low number. Now I run it for 1,000 samples. Sorry, 10,000 samples. It's much better. This really resembles the true beta posterior, but it's only because it's a toy example. Here it is, 0.6. So it really resembles. It's not so precise, but it's much better than those 1,000 samples. We have, where is it? We have 1,600, so nearly 1,700 effective samples, which is very solid number for plotting a histogram at least, and for making a smooth line approximating the true density. So this was answer to Anton's question. There are 5 times that you can open only one A, and B. Question for the audience. Please, can anyone of you send to Slack whether you can open other files like 1B, 2A, 2B? Or should I investigate where the problem is? Because I believe the files are no. So you can't access the files. Strange. 1B, it's there. If I click at it, I would need to wait. Everything works locally. Yeah. Great. Perfect. Thank you. Thank you so much. So then I will close this. What you need is to download or pull from the repository and open it locally. They are hanging on the server. They shouldn't be hanging locally. On the server, it does not work because there is some problem in the GitLab, and it's rendering of Jupyter notebooks. It's problem connected with the GitLab, not with the notebooks themselves. Yeah, just Daria, just locally. It does not open or remotely. It's not impossible to open it remotely because there is some bug in GitLab. Well, great. So what we know, oops, now I have some local rendering problem. Oops, and where is the problem now? seems that there is, here it is. No, it is not. Something happened. So I will reload the tab. I'm sorry, but something happened with my browser. So I will stop it, reload it, and hopefully it will work. Well, let's wait for rendering. What we can change is it's not only the number of samples, but also the form of the prior. I already told you that we have a beta prior, very flat beta prior for the mean. What will happen if I use some other prior? Let's say that I will use some inconvenient prior. P uniform from 0 to 0.4. If you remember, I told you that if the prior does not cover the true parameter value, the posterior should converge as close as possible, but then it will stop. So let's try with the uniform from 0 to 0.4. The true value is 0.7, so it's not covered. And let's look what will happen. It still compiles. Still it compiles. In the meantime, I will check our Slido. So, value error. Sorry, I forgot the semicolon. I use Python so much that I forget the semicolons. Any new questions, Slido? Nope. So come on, come on. The compilation is sometimes a very long lasting task. It's eternity. So come on. This is the problem, by the way, if you are talking about, say, probabilistic programming, because once you run MCMC, you can go for a cup of coffee during the lecture. So come on. Here it is. Great. The sampling should be quite fast because it's in C++. You see, there is a warning. The sampling from the uniform limited from 0 to 0.4 is very ineffective. Many iterations ended with the divergence. And there is another warning, try running with adapt delta larger than 0.8 to remove the divergences, but it won't help because the prior is very badly chosen. You see the mean 0.4, standard deviation very tiny, which means that the posterior distribution is concentrated in the end of the uniform distribution. It's between 0 and 0.4, and the mean is 0.4, and the standard deviation is very, very tiny. If you plot the result, bang, this is how it looks like. very concentrated on 0.4 because it would prefer to continue to the right, but it's not possible. The prior does not cover more than this interval. So that's the problem. Well, this demonstrated also that if there is a problem with convergence, stan will rise an exclamation. If there is a problem with a few samples, you will see it from the shape of the posterior. The posterior should be relatively smooth line. So that's it. No new questions. Okay, I will move to example 2. In this example, we will use a real data set, and we should estimate the mean and standard deviation of a normal Gaussian distribution. The data set contains the housefly wings, wing lengths. Housefly, do you know what housefly is? It's this stupid insect. Housefly. It's quite known that the housefly wing lengths are very close to normal distribution. If I load the data and plot a histogram, it looks like this. Very nice picture, symmetric. Mean is 45.5. Nice standard deviation, very nice picture. 100 samples there. So the frequency statistics would calculate the mean and the standard deviation. A natural question is, how can we be sure about the mean being this number and about the standard deviation being this number just from 100 samples? Only 100 samples. If you meet 100 people and they tell you their salary, would you state, well, this is an average salary of the population? Probably not. The same about the standard deviation. 100 samples, it's not very much. So the question is, are these estimates precise? What is the uncertainty about the mean and standard deviation? We have a relatively small number of data. If we summarize it, I said that the wing lengths follow the normal distribution with some mean and some variance or standard deviation squared. And I want to estimate this mean and the sigma. It's quite usual to estimate the mean of a Gaussian distribution using another Gaussian, because the mean may be, if the mean may be positive, negative, unlimited, then the then the Gaussian distribution is 2. The standard deviation itself is a positive number, and it's quite usual to estimate positive numbers, positive real numbers, using a gamma distribution. So we have a model for y, for observation for the housefly wing lengths. This is a normal distribution with 2 unknown parameters, and these 2 unknown parameters we estimate using normal and gamma prior distributions with some hyperparameters. So the question is how to choose the hyperparameters here and here. The hyperparameters for the mean, well, we can guess. The hyperparameters for for sigma is, that's the hyperparameters of the gamma distribution. It's somewhat more complicated. You can read the paper from Lambert et al. How vague is vague simulation study, or the impact of the use of vague prior distributions in MCMC using Winbugs. Winbugs was a software like the Stan. So the question here is how to choose the hyperparameters of the gamma distribution so that the gamma distribution is non-informative, so that it's not too narrow, so it doesn't carry any prior information at all. The model code looks like this. We have n data points, which are high. Parameters are mean, mu, and standard deviation. These are parameters of the model. And the model is normal with mean mu and standard deviation STD. We estimate the mean mu using normal distribution. I opted just for the mean 50 and the standard deviation 100. Recall 100 standard, if it's a standard deviation, then 3 standard deviations around the mean cover approximately 99.8% of data. So it's like 50 plus minus 300. So it's very flat. And the standard deviation of the model, data model, is estimated using gamma distribution. I should choose here something like this and something like this. This is non-informative, which I know because I do it for some time. So we compile it. I hope I run this. So we will compile the Stan code. I'm quite curious whether those of you who live more to the east from me are tired too, because I feel I start to be a bit off. So it still compiles. Come on, come on. Fortunately, or I hope that you don't hear the fan of my laptop. The laptop is very hot. So it seems that the fans are slowing down. Here it is. Perfect. This. I run the sampling again, 100,000 samples, and the mean, the estimated mean has, well, this is mean of mean. The posterior distribution for the mean has expectation 45.5. So I would say that the mean of the housefly wing length is 45.5 with a standard deviation 0.4, which means that between 44.71 and 46.29 lies 95 lies the true value of the housefly wing length with probability 95%. The standard deviation of the housefly wing length is 3.95. And again, the true value lies between 3.44 to 4.55 with probability 95%. One of the most complicated things is to correctly express what we realize, because we have posterior distributions for something, and if it's a posterior distribution for a mean mu, it itself has a mean, so it's a mean of mean. So it's expectation, better, maybe better to say it's the expected value for mean mu. If I plot the posterior distributions, they look like this. This is for the mean of housefly wing lengths. Here I can see 45.5 is the mean value, if I remember yet. And here lies the 95%, or with a 95% of probability, the true mean lies in this region. The standard deviation looks like this. It's slightly asymmetric because it was from the gamma distribution, which is asymmetric itself. And the mean is 3.95. So the mean is somewhere here. If we obtain new measurements, we can use the posterior distributions and just update them. They should be stored, and we can just exploit them. You may try to set a misleading prior distribution. For instance, to set a wrong distribution for the mean, for, say, very concentrated on a region far from the true mean. If I do this, the true mean is 45. I can say that it's just 5. It's standard deviation of 1. Again, we need to compile it, so it will take some time. This is a very concentrated prior distribution. The true mean is 45.5, and I say prior distribution for it to be located at 5 and very narrow. So let's wait for compilation. Roman, I do hear it, but only slightly. Ooh, I didn't change any setting. Does anyone else have a problem with hearing, with understanding? Well, it seems that fans are slowing down again. Here it is. So, improperly set prior. Mean 7.62. Standard deviation still around 1, so it can't change a lot. Everything is clear. Great. And here we can see the result. The mean is the estimated mean is totally meaningless. No problem. Great. What we can see is that if the mean is misplaced, then the standard deviation is incredibly high, between 30 and 48. Do you see it? Standard deviation 38.38 estimated. So the housefly wing length is estimated to be 7 millimeters, 50 millimeters. It's like 0.7 millimeters, and plus minus 3 times 38. So plus minus 10 millimeters. It's complete nonsense. So you very often you need to just use some logic for the problem. I hope you see it. What I really don't like about this online teaching is that I don't have an immediate feedback. So I hope that this is clear. Thanks to all regarding the sound. So this was the estimation with misleading priors. The third example, and this is the last one, is modeling time to event using, and we will check the posterior predictive distribution. Say that we have a detector that observes a particle flow. The particles arrive independently and at a constant rate. This is a very frequent scenario if you have, say, a solar probe and it's bombarded by solar particles, and it's relatively constant in a short time. The time between two consecutive detections is described by data in the file. It's time to even NPZ. And the goal is to estimate the rate parameter. Generally, if we model waiting times of such processes which are independent, we use the exponential distribution. If you are familiar with statistics, you are probably familiar with this. The exponential distribution has a rate parameter lambda, which is non-negative real number. And the task is to estimate this lambda from these measurements. If you look at the histogram of the measurements, it looks like this. These are the waiting times in microseconds. I think microseconds. So it's distributed like this. Most is within 0.01, and then the probability decreases. It resembles the exponential distribution. If we fit the parameter lambda, we may want to calculate the posterior predictive distribution, which is a distribution that predicts where the true measurements could be expected to lay. So it will give something like a confidence region for each measurement, and this confidence region is in fact the 95%, the highest probability density interval. And it says with probability of 95%, the measurement should be within the interval. The predictive distributions or posterior predictive distributions, there should be given, there is a mistake, sorry, lambda given y1 L dots yn. So we have a posterior distributions for our parameter lambda, and we want to predict where we can expect the new or past measurements lay with probability of 95%, say. So for this, we have a predictive distributions which is obtained by multiplying the model. This is the model, the exponential density, times the posterior, and we integrate the parameters out. The posterior predictive distribution is not conditioned by any parameter. It just says, based on past observations or based on available observations, y1 to yn, my concrete distribution y will be described by this probability density. And probability density means it's some distribution from to some number concentrated mostly around some region. It may be used for predicting the future number, the future realization. Well, the code looks like this. Again, I have n data items are the data themselves. The parameter is the lambda of the exponential distribution, the estimated rate parameter. The model for the observations is exponential with the parameter lambda, and the parameter lambda I estimate using the gamma prior, very flat prior distribution. In addition, I have one more block here, the generated quantities. Generated quantities are calculated as the sampling proceeds. What I want to generate is y hat, the predicted, here is y tilde, there is y hat, doesn't matter. The predicted y for each y, for each of these, for each of the n observations, generate the predictive or predicted y hat by sampling from the exponential distribution where we plug the lambda posterior. This is the posterior for lambda. We plug it into the exponential distribution and sample from the rest. Yes, I will. That was a question from Veronica. So, was it already compiled? I hope so. Now I feed it by my measurements, just 100 measurements, but I will do 100,000 iterations, and it will calculate the posterior distributions, posterior predictive distribution. So sometimes it may take time. Here I want to print summary. If I will show you, if I don't limit to lambda, it will print the posterior predictives for all those y's, for all those 100 data samples, 200. So I want only for lambda. So the estimated rate is 52.41 seconds, milliseconds, microseconds, I don't know now. The standard deviation is 3.7. So the true value of rate lies between 45.38 and 59.86 with probability 95%, the mean being 52.41. In order to plot the results using ARVIS, we need to be slightly more precise in defining the inference data from this. So from Python, we extract the posterior. The posterior predictive are those y hat. And in order to plot the posterior predictive, I need to state what observed data are. This is the posterior distribution, not the predictive distribution, but the posterior distribution for lambda is the estimate of lambda. Here is the mean, those 52.41. Somewhere here is the mean. And this covers the true value of lambda with probability 95%. The posterior predictive, it will be plotted within a short moment. The problem is that the distributions are represented by samples. So the posterior, in order to plot the posterior predictive, well, we need to plot it from many samples for each of the observation y. So come on. Come on, come on. Come on. Well, I can answer to Roman's questions. It was in regards to the font noise. Sorry for confusion. Is there a way to make compiling a tad faster? It's 47.1 seconds on i7. I also noticed that it's heavily single-threaded. So is there a way to compile C++ in the multi-threaded mode? Well, the problem is, Roman, that the MCMC principle is sequential. It's a 1-4 cycle. So it's you are at one point, you sample another point, you move to that point, you sample another point, you move to that point, etc., etc. So you can't parallelize it. The way to parallelize it is to run multiple chains and just join them together. But these may end with slightly worse results. So the biggest problem with MCMC is its sequential nature. It can't be well parallelized. Hope it answered your question. Well, here is the posterior predictive. If you look at the figure, we have observed y by, it seems like, black line. These are those observed values. The blue line here is the posterior predictive mean. Posterior predictive mean. It's in fact the mean of the exponential distribution, sampled exponential distribution. And the brown region shows where the posterior samples are expected with I think 95% of probability. So if your true observations, if the black line were close to to margin, one or a second margin of the band, or if it even were outside the margin, then you know that the posterior predictive distributions is not correct. It doesn't explain your data. The posterior predictive distribution should explain the data. If it does not, then it means that either the estimated parameters are wrong, or more likely the whole model is wrong. You may try to set some inconvenient prior, for instance, uniform on 0 to 10 for lambda. So instead of gamma, I will use uniform 0 to 10. Oops, semicolon. Yeah. The true or the estimated value, the estimate was 50, near 50. I know it's 50 because I have it here in the title. So if I set uniform from 0 to 10, it really does not cover the value 50. And we can see what happens. This will be the end of the lecture. So if you have any questions, hurry. So again, compilation. Come on. Still compiling. And now imagine what would happen if we simulated the Markov chain Monte Carlo directly in Python. it would be something terrible. So it's a good thing that someone wrote this software. So sampling, you can see that if you generate some quantities like the posterior predictives, it takes more time, naturally, because you need to run extra chains. So the mean is 9.94. The limits of the uniform distribution were 0 to 10. So it's very close to 10. It would be happy to move to 50, but it can't. Do you see it? Ah, 10. I want more, but I can't. And posterior predictive. Now we need to wait for it again. Come on. My laptop gets very hot. And now imagine that there are people that are simulating a very complicated, that are estimating very complicated models. One of my friends works on data from radiation protection, and his models using some analytical approximations are estimated over the whole night. And he told me that if he tried to do it by MCMC, it would take three days to get results. Unfortunate is that after those 3 days, you don't know whether the results are okay, because you may realize that there is a problem in your model, and that this means that, wow, another 3 days of simulations. So it's a good tool, provided you are very careful. So this is our posterior predictive. The black line represents the true data. If you look at the histogram, then it will. This is a smoother histogram. The blue line represents posterior predictive mean, and the brown region represents the posterior predictive distribution. It's, say, 95% of highest probability density. We can say that the posterior predictive really does not express our data at all. So based on this, we can say that something was wrong, either model or the priors. In this case, it was the prior. We can assess it from this figure. It would like to converge somewhere to the right, but it stopped at the margin of the prior distribution. Here, tomorrow I will talk about MCMC, and here you can assess, you can guess that there is some sampling problem, because it stopped there. I want it to go over 10. Well, and that's it. So in order to estimate the model, you need to choose a convenient prior, check the results, the mean, the standard deviation. Here you don't see that there is a problem because Stan doesn't say anything. It's happy with art. But then you see the posterior distribution and see that there is some problem. You see the trace plot. There is again a problem because the line should be hairy above 10 too. And if you plot the posterior predictive, you see that it doesn't fit the data at all. So there is something wrong. And that's it. I will try to share video. But, oh, well, doesn't work. Does it work? Yeah, it does work, but there's...
Yes, we see you at last.
So great. This is everything from me. It seems that there's nothing in Q&A. So we will meet together tomorrow. Pirate.
Okay. See you then tomorrow. Thanks for this lecture.
So, bye.